Hi, welcome to Temaher Tube. In our channel we will present you some concepts in civil engineering and related fields. In this video I will introduce you to the moment distribution method, which can be used to determine the bending moments of beams and slabs in a frame under distributed vertical loading. According to Wikipedia, the moment distribution method is a structural analysis method for statically indeterminate beams and frames developed by Hardy Cross. It was published in 1930 in an ASCE journal. The method only accounts for flexural effects and ignores axial and shear effects. From the 1930s until computers began to be widely used in the design and analysis of structures, the moment distribution method was the most widely practiced method. To show the concepts of moment distribution method, we will consider the frame system shown in the diagram. The frame is loaded with a distributed load Q equal to 100 kN per meters. The beams have a dimension of 400 mm width and 500 mm height. The exterior columns have a dimension of 400 by 400 mm. The interior columns have a dimension of 450 by 450 mm. The length of the beams and columns is also depicted in the diagram. A concrete class of 35 MPa will be assumed. Using the formula shown, the concrete will have a Young's modulus of 26,622. First, we need to determine the moment of inertia of each frame element. The moment of inertia can be calculated by the formula B times h to the power of 3 divided by 12. In the next step we will determine the stiffness of each element. For beams and columns with ends, the stiffness of beam and column members can be calculated by the formula 4 times Young's modulus times moment of inertia divided by length. Now we need to determine the distribution factor at each joint. The distribution factor is a relative measure of the stiffness of a member at joint relative to all other members at a joint. For example, at joint B, the distribution factor for the member BA will be calculated by dividing the stiffness of the member BA to the sum of the stiffness of all other members at the joint including member BA. We need to calculate the distribution factor for all joints and, in every direction. In the next stage, we need to calculate the fixed end moments assuming each span behaves individually. For fixed connection, the fixed end moment equals distributed load Q times length of beam to the power of 2 divided by 12. We need to calculate the fixed end moments for all the 3 beams. In the moment distribution method, every joint of the structure to be analyzed is fixed so as to develop the fixed end moments. Then each fixed joint is sequentially released. When a joint is released, an unbalanced moment will occur at joint. We need to balance this unbalanced moment by adding an opposite moment equal to the unbalanced moment. This moment will be distributed to each member at the joint based on the distribution factors we determined earlier. When a fixed end member is released at one point and a unit moment is applied, the carryover factor to the opposite end amounts 0.5. Now we have determined all required parameters to determine our moments. Notice that the fixed moments have different signs at the left and right of a member even if they are both negative moments. This should be maintained during moment distribution. Now we will start the first step of moment distribution. We will begin at join A and advance to the right. As you see, we have only a moment equal to 208.33 at the start of the beam. The column has initially no moment. When we release joint A, we have an unbalanced moment of 208.33 kNm. For the beam member at joint A, we need to add the opposite of this moment multiplied by the distribution factor of the member at joint A. Similarly, for the column member, we need to add this moment multiplied by the distribution factor of the column at joint A. Now we need to carry over the balancing moment to the opposite members with a carryover factor of 0.5 as discussed earlier. We will do this only for the beams, hence we are interested on the beam members. In the second stage of the first step, we will jump to the joint B and release this joint. As you see, the amount of moment we need to add for balancing at the joint equals the sum of the moment that is carried over from joint A and the fixed end moments of the member BA at joint B and the member BC at joint B that we calculated previously. In a similar way, we need to add the opposite of this moment multiplied by the distribution factor specified at the joint. After balancing, we need to carry over the moments need to balance the joint to the opposite ends of the members. Then we move to joint C and will do the same. Then we move to joint D and will do the same. Now we have completed the first step of balancing. You see all the balanced moments in the first step in green color and the moments that are carried over from adjacent members in black color above them. Now we start step 2 at joint A similar to step 1. We balance the moments and carry over the balancing moment to joint B. We repeat for joint C and D similarly. Now we have finished step 2. You see all the balanced moments in the second step in cyan color and the moments that are carried over from adjacent members in black color above them. Now we repeat the procedure for the third time. We have to do the iteration until the solution converges or the carryovers are too small. Since the third step is my last step, I won't do the carryover backwards. You see all the balanced moments in the third step in orange color. There are no carryover moments since we have decided 3 steps are sufficient. Now we have to add all the moments at each joint together. This will give us our frame moments. The final results are shown in this diagram. The moments along the span can be calculated based on the moment of simply supported beam MO and the moments at the left end and the right end of each beam element. For comparison, I have here an image from finite element analysis with RFEM6. The beam moments are consistent with our earlier findings. As in the example, you can determine the moments for beams and slabs using moment distribution method, in case you don't have access to finite element software. Thank you for listening. Subscribe and stay tuned for similar contents. Temaheart Tube.